Hi everybody. This video is going to be on section 10.3, periodic functions and the Laplace transform. Okay, so let's talk about periodic functions. You guys have seen periodic functions for a long time, probably ever since you took a trig class. Let's define it formally. So a function f defined on 0 to infinity is said to be periodic with period t. So periodic with period t if t is the smallest positive real number such that f of t plus capital T is equal to f of t for all t greater than or equal to 0. So another way of saying this is something is periodic with period t if the graph just keeps repeating itself, and one full cycle, we call that a period, is of length capital T, okay? It's the smallest positive real number that works. So just so we could see a simple example of this, let's let f of t be a piecewise function 2 if t sits between 0 and 1, and 1 if t sits between 1 and 2. And furthermore, f of t plus 2 is equal to f of t for all t. So what does this graph look like? Well, it's switching off between 2 and 1. So if this is 1, 2, and this is 1, 2, what we see is that we're going from here to here, and then we're going from here to here. But because of this repetition here, this is saying that it's going to keep repeating. Right? And this goes in the other direction too. So why do we call this guy periodic? Because it's the same graph repeated over and over and over. And so what would the period be? The period, so f is periodic with period equal to 2, right? Because it takes 2 each time to do one full cycle. That's how long it takes to repeat. Okay? All right, so why are periodic functions interesting? Well, when it comes to Laplace, they behave really nicely. Okay, so let's do a theorem here. Suppose that f is of exponential order. Okay. If f is periodic on 0 to infinity with period capital T, then the Laplace of f is actually equal to the integral 0 to infinity. The Laplace of f is actually equal to the following. This is really cool because this is saying that we actually don't even need to integrate all the way to infinity. Because it's periodic with period t, our integral only has to go from 0 to t, and we end up getting, just this little factor that pulls out, okay? Oh, there is a typo here. I apologize. This should be negative s capital T, right? Because little t is a dummy variable. That's never going to come out, okay? I would like to prove this. It's a really interesting proof as to why this is true. And really, this is a short section, so this proof will be an interesting result that proves this theorem. So let's write down proof here. I want to show you guys how this works, okay? So the Laplace of f, well, we know by definition that this is going to equal 0 to infinity, e to the negative st, f of t dt, right? However, what if we split it up at the period? Okay, so what is this going to look like? So if we split this up at its periods, it looks like this. First, we go from 0 to capital T of e to the negative st f of t dt plus the integral from, then we go from capital T to 2t, e to the negative st f of t dt. And then let me do one more. From 2t to 3t, what is the nth one going to look like? So the nth one, of course, would be, we're going from n t to n plus 1 capital T, and then e to the negative st f of t dt, right? So what I want to do is give these each names. So what I'm going to do is I'm going to give these each names, okay? So I'm going to call this first guy I0. I'm going to call this second guy here I1. This guy is I2. And this guy right here is actually IN, right? And so we're adding these all up, right? So what I want us to do is actually solve what these guys would be and then plug it back in, okay? So here's what we are seeing so far. So what we're seeing is that the Laplace of f is actually going to equal the sum of n equals 0 to infinity of IN. So the whole point is if we can figure out what IN is, then we should be able to plug it into this and then see what we get for the sum, okay? So what does IN equal? Remember, IN is exactly the integral from n capital T to n plus 1 capital T e to the negative st f of t dt. So the trick here is to do a u substitution. We're going to scale it back. So I'm going to let u exactly be t minus nt, like this. Okay. And what would du be? Du would just be dt because all I'm doing is scaling this back, but the derivative is still just 1, right? Because nt is a constant. And so this is going to become, what's my new integral going to become? So if I take nt and I plug it in for t, that means I get nt minus nt is 0, and then I get m plus 1 capital T minus n capital T is just t, right? Capital T. And then this becomes e to the negative s times, remember lowercase t though, lowercase t is equal to u plus n times capital T. So this becomes u plus n times capital T. And then we're going to get f of u plus n capital T du. So we've changed our integral to u. However, this is where we use the fact that f is periodic, right? Since f is periodic, isn't this the same as f of u, because we're just adding n periods to it? And we know that everything, f of u is the same as f of u plus t. We just keep applying that logic, right? So what do we end up with here? So this is equal to, from 0 to capital T. I'm going to write it this way now. E to the negative su, e to the negative n capital T, and then I have f of u du. Okay, so this is where we are right now, and what I'm going to do is I'm going to pull out this, sorry, I forgot the s here. Let me fix this. This is negative snt, right? So I pulled that out because that does not have any u's in it, right? So I could pull that out of the whole thing. So I get e to the negative s and capital T, and I'm left with 0 to capital T. And then I have e to the negative su, f of u du, right? Okay. So what does that mean? So I'm now going to use that formula. So here's what we have learned, right? What we've learned is that this is equal to this. And so what I can do now is I can put it in my sum, right? So let's go back to our sum up here, right? This is what I mean. I'm going to replace my in with that now. And so this is what I get. I get that the Laplace of f is equal to the sum from n equals 0 to infinity of exactly what I got for this guy right now, which is e to the negative s and capital T, integral from 0 to capital T of e to the negative su, f of u du. Okay? Now, next thing to notice, this guy doesn't depend on n, doesn't? The integral part doesn't, okay? So that means the integral can get pulled out. So if we pull the integral out of the sum, this is what we end up with. We get the integral from 0 to t of e to the negative s u. Now, here's the thing about that. I could just replace this with lowercase t's because it's a dummy variable anyway, right? So let me just go ahead and replace that now. And what I'm left with is the following. N equals 0 to infinity. Now, watch the way I write this. Isn't this term that I double underlined the same as this? It is, right? Just by exponent rules. However, this now is a geometric series. Remember, a geometric series always equals the first term over 1 minus the ratio. Okay? So this is going to equal, this guy right here actually equals, the first term is 1, and then we have 1 minus, the ratio is e to the negative s capital T. And so I get this integral times that constant, and I'm going to pull that constant out in front, and then I get exactly this. Okay, and we get our result. Okay, so this is the proof. And by the way, something some of you might remember is that the geometric series only converges if this is true, right? The absolute value of the ratio is less than 1. Okay, but what does this mean? So if I were to take the natural log of both sides, I get that the negative st is less than 0, right? But what does this mean? Well, since t is positive, this must mean that s is bigger than 0. Because if negative s is less than 0, then this means that s is bigger than 0. Okay, so no problem. We've got s is bigger than 0 here, and this ends up being our Laplace. So we've got our results. This is the proof. And now we have a way to deal with any periodic function. Very, very cool principle. So I would like to do an example. So I want us to let f of t be the following function. Sine of t when t is between 0 and pi, and 0 when t is between pi and 2 pi. And then we're also going to say that f of t plus 2 pi is equal to f of t for all t. So what does this look like? This is a periodic function, okay? But in particular, what's happening, we're using sine from 0 to pi, but then we use 0. So if I was to use so this is what we get, right? We keep getting something like that. These are supposed to be sine waves. I apologize, it doesn't look great. But from 0 to pi, and then 2 pi, and then 3 pi, and then 4 pi, and so on. So what would the period here be? Well, it should be obvious by the definition that this is periodic with period equal to 2 pi. So this means that capital T is equal to 2 pi. Okay? So what I would like us to do is to calculate the Laplace inverse, or sorry, not the Laplace inverse, the Laplace of f. Okay? So let's calculate the Laplace of f. And of course, we're going to use the theorem that we just did to help us, right? So let's remember what the theorem says. The theorem says, so let me go to the next page here. By the theorem, the Laplace of f is going to equal, now remember it was 1 over 1 minus e to the negative s, and then we had the period capital T, which in this case is 2 pi. So let me write this as 2 pi s. And then all we have to do is find the integral from 0 to capital T, which is 2 pi of e to the negative st f of t. Okay, so really all we need to figure out is this, right? So what would that equal? Well, the integral from 0 to 2 pi of e to the negative st f of t dt, this is equal to, can't I go from 0 to pi first and then go from pi to 2 pi? Okay, but from 0 to pi, that's sine, so it's going to be e to the negative st sine of t dt. And I don't really need the other one, I'll just write it down here, but remember, I don't need it because this is going to be 0 anyway, right? That was how our function was defined for that piece, so we don't really need to do that. So all we really need to do is figure out what the integral is from 0 to pi of e to the negative st sine of t. Okay? So what do we end up with? It turns out this is actually an integration by parts problem. And I don't want to do this from the beginning because it is time consuming here. But the trick is to let u equal e to the negative st, and then dv is sine t dt. And then this means that du is negative s e to the negative st dt. And v is equal to negative cosine t, and then you use integration by parts on that, and then you get something, and then you use integration by parts again, and it becomes one of those wraparound integrals. And so you do it again, so I'll just say parts twice, and this is what you end up getting for that integral. You end up getting e to the negative st times negative cosine t, and then minus s times sine of t, and then we get we have over 1 plus s squared. Okay, so this is what we get, and then we have to evaluate it from pi to 0. And what do we end up with here? So if you plug in pi and you plug in 0, we actually end up with the following. This is equal to e to the negative pi s plus 1 over 1 plus s squared. Okay? Not sure why I put those brackets there. However, all I have to do now is multiply it by this, right? Because that's next to the integral that we just did. And so what we end up with is the following. We end up with the Laplace transform of f is equal to, remember we pulled this guy out, 1 over 1 minus e to the negative 2 pi s, and then we multiplied it by e to the negative pi s plus 1 divided by 1 plus s squared. However, something nice does happen here because this bottom guy can factor, right? This is a difference of 2 squares. This is 1 minus e to the negative pi s times 1 plus e to the negative pi s. That's what this guy became, and so this guy actually cancels with this guy, and so our answer to the whole problem is 1 over s squared plus 1 times 1 minus e to the negative pi s. Okay, so this is our answer. Very cool theorem. It allows us to find the Laplace transforms of any periodic function. Okay, finally in the next section we're going to learn how to solve initial value problems using the Laplace transform, which is the whole point of the chapter. So I look forward to you guys watching the next video. Thanks so much for watching. Hope it was clear. Have a good day, guys.